Hey everyone, so what this video is about is actually going over some sample incline plane problems as well as some sample kind of friction problems, and we'll actually kind of combine the two together. And so really, we're going to jump in and look at problem 52 here, which is actually one of our homework problems, I believe, and just kind of jump in by looking at like what the heck is being asked of us here. So we have a block kind of in this picture here. It's on a smooth plane, angled at this angle 22 degrees to the horizontal. So that's kind of this little theta guy down here. And we're being asked to determine the acceleration of the block as it slides down the plane. And then if the block starts at rest, so that's the initial velocity is 0, this far up the plane, what will be the speed when it reaches the bottom? So we know how far it's traveling is that 9.1 meters, really. So how the heck do we do this? How the heck do we even approach it? So in the case of this one, well, we know that gravity is really just pulling straight down here, right? And if we had a non-perfectly smooth surface, well, we'd have some friction going kind of up and up the plane resisting. But this says it's on a smooth plane, and it even says again, ignore friction. So essentially we're doing this with no friction. It should kind of make it a little easier, kind of separate, kind of remove the friction portion from it. But let's look at part A here really. So for part A, it's saying find the acceleration. Well, the first thing I want to do, even though we have it here, is I'm going to draw a picture. I just want to draw a picture and get my head wrapped around what the heck is actually going on here. So I'm just going to draw my plane. It doesn't need to be perfect. And then on my surface of my plane, I'll just have my box here. And again, we have really this force of gravity is going kind of straight down from it. And this is the gravity kind of acting on the block. And then they say that it's smooth. So we're ignoring friction. So there is no friction kind of acting uphill. That's not there. But we do, in fact, have a normal force. The normal force is absolutely present, and it always presses directly up off the surface. So if this normal force were to go all the way down here, we'd have like a little 90-degree box there. If you want to kind of add that as well, you totally may. Now, we're given that this angle here is 22.0 degrees. So that really tells me, and this is from our notes for inclined planes, that really, if I were to kind of break this down and kind of do a little dotted thing going back down here, that really this is kind of my part of gravity that's acting perpendicular to my plane. So my plane's here. So really it's at a 90 degrees to it. This is kind of my force perpendicular. That's what the little upside down T is. Or maybe we're lazy and we call it force perp. And then we kind of have this part going this way. And this is really the part of gravity that's acting in the parallel direction. The two little bars next to each other means that it's parallel. And so the neat thing is from our notes, we know that if this is 20 degrees, we know that right here, this is also our 22 degrees. So we totally know that really is kind of the whole idea. And so if you're like, wait, how the heck do I know that this angle is the same as this? Go back, watch the notes on it. You don't need to know how to prove it, but you do need to know that you can always draw the perpendicular kind of part of gravity going straight down perpendicular off the plane. And then draw the angle between that perpendicular and gravity is that same angle really, okay? So with that in mind, if I know an angle and I have a triangle here, that always tells me, kind of like in Unit 1 with our projectile motion stuff, that, hey, I better find these two components because that's the easiest first thing I can do. And so in this case, I can just go ahead and start solving for that. Now, I also want to mention that since my box is not jumping up off the plane, kind of accelerating up into the air, and it's not going through and crushing through my plane either, the perpendicular part of gravity here in green and the normal force, those are equal but opposite. They match each other. They cancel each other out, right? Otherwise, it would be accelerating in one of those directions. And since there's nothing going really uphill here, that means that actually this perpendicular component of gravity is the thing that's going to make my block accelerate. really, this is the only force that's left over. So this is really my net force here. This is our net force. And so I might make a little note here saying that really, since the force of friction is 0, that's because we ignore friction. They're essentially saying mu is 0, right? Well, then our net force is just this parallel part of gravity is the whole idea. So now let's actually go about solving. So if this is my angle, well, the opposite part of it right here is the blue. And so we know TOA, sine is opposite over hypotenuse. So if I use sine, that's going to get me my parallel part right here. So I have sine of my angle is going to be my force parallel divided by, well, force gravity. That would be the hypotenuse of this triangle, okay? And so we know that Fg, the force of gravity, is really just mg, right? And so hopefully we can just go ahead and say then that mg times sine of my angle, which is 22.0, is equal to my force parallel. That's kind of the whole idea here. And so again, the real trick that I did to get this last step is I just said that I know this Fg, I can just multiply it over right here. And I know that Fg, the force of gravity, is just mass times gravity, okay? Now, a neat thing to kind of note is they did not give us a mass anywhere in here. So I have no freaking idea what this m thing really is, which is kind of an odd thing. But we kind of have an expression for this. Now, we also know, though, since our net force is this parallel component, well, we know Newton's second law. And Newton's second law tells us that the net force is equal to the mass times the acceleration. So really what I can do right now is I can say that this mass times acceleration is equal to this. And the reason being is because this kind of algebra expression here is how we represent the parallel part of gravity, the part of gravity that's acting parallel to the plane or parallel to the plane, really. But that is our net force. That's our leftover force. It's the only thing that's not getting canceled out. So I'm just going to set these two equal to each other. So I'll have mg times my sine of 22.0, I should probably put some parentheses on it, is equal to mass times acceleration. And lo and behold, mass and mass cancel, which is pretty incredible, right? And so now we know g is 9.8, so I can actually just plug in now, because we're being asked to determine the acceleration of the block. Well, now a is alone here, which is pretty convenient, pretty nice. So if I do 9.8 times sine of 22.0 degrees, I end up getting a 3.67. But since g only has 2 sig figs, well, this 3.67 would just become 3.7 here. Let's make a little more space. 3.7 meters per second squared is equal to our acceleration. So that is how we did part A. Now, I will say, if we were not ignoring friction, well, mu would be some number like, I don't know, 0.2 or something. Well, then we would have friction going uphill, and we'd end up having to kind of write out the net force in the direction. We'd say that, well, it would be this force really like minus force friction, and we'd have to solve for whatever the heck this frictional force is. And we'll look at that actually next after we finish this. So now let's look at part B. So part B here, they tell us that if the block starts this far up the plane from the base, what will be the speed when it reaches the bottom? So really, they're asking us, what the heck is v, the velocity of it, but then forget the sign is really what they're saying. And you could probably say that, well, let's say the positive direction is up, kind of straight off the plane. And let's say the positive direction is like kind of this direction down the slope. It starts being a little weird if you're saying positive is just up and positive is to the right, because then if something's moving down at this angle, well, you end up having to like do the Pythagorean theorem and find like, oh, well, what part of it's going downhill and what part's going to the right? And it's actually more math that you have to do, in all honesty. So really, let's find the speed at the bottom. Now, if I am being asked to find a speed, that makes me think unit 1. That makes me think of these equations right here on our equation sheet. That makes me think of these 3 right here. And so what I want to do is take these 3 and we'll kind of put them down over on kind of our sample problems right now, and we can kind of look at these and see which ones may be the most appropriate. So in our case, really looking here, well, we know it starts from rest, so we know that the initial velocity is 0 meters per second. We know that we get to call wherever it starts 0 meters. We also were told it starts 9.1 meters up, so we know this is 9.10 meters. And now we know the acceleration. We just found it. So A is 3.7 meters per second squared. Now, I don't see a time that I was given here. So that's something we don't know. Because really, this guy looks nice and easy. We know this thing is 0. We know A, but I have no idea what the time is. So if we could find time, we could plug into this first one. So let's keep going. This second one, well, we know what this is. It's 9.1. We know we get to call this 0. We know it starts from rest, so this whole thing is 0 as well. And we know the acceleration. So if we know x, how far, we know the acceleration, we could totally get time from this second equation. We could do that and then plug that time value in right here, and then we would have our speed at the bottom. That would totally work. But let's keep looking just to see what our third one would be actually here. Well, we want to find the speed at the bottom. We know it starts from rest, so that means this thing is 0. We know the acceleration. We know this value is 9.1. We got it right here. And we know this is 0 as well. So actually, I don't need to use 2 equations. I see that I could just use this third one here and we would be done. Everything would be kind of hunky-dory and great. And so let's just use the third one. You can totally use the other method, but this looks easier to me. So our final velocity squared is equal to 0 plus twice the acceleration, which is 3.7 meters per second squared, and then times our x, which is just 9.10 meters. Well, I end up getting then that our velocity squared should be, what is this? 2 times 3.7 times 9.10. I get 67.34, 67.34, and we have meters times meters, so that's meters squared, over seconds squared. And we go, whoa, this has 2 sig figs, this has 3 sig figs, this has kind of infinite sig figs because it's kind of that perfect 2. So our answer in the end should have only 2 sig figs. So let's take my square root and then we'll round appropriately. So I have the square root of that guy is 8.20. So I get that we have 8 point, but we should have 2 sig figs. So 8.2 meters per second, because square root of meters squared gives us meters, square root of seconds squared gives us seconds, and then we are actually done. We found the speed it will reach once it's traveled this full 9.10 meters. So that's really it. That's how we would go about doing this. If there's no friction, I'm just going, how the heck do we set this up with this plane now? And it really comes down to having to always break up gravity into the part of gravity that's going in line with the plane. So it's parallel to it. So that's our force parallel here. And then the part of gravity that's going perpendicular to the plane. And so that's really what this force perp in green really is, okay? So what I want to do now is I actually want to look at a problem that I'm not asking you to do, at least I don't think so. And I want to look at this one. It's 54 in the book. It says, repeat the problem we just did. But if mu, the coefficient of friction, is 0.20 between the block and the plane. So how the heck would I do that? So let's pretend really here, let's just go through, let's do the whole thing again. All right, so I'm just gonna move this guy over. We're gonna take all this. Actually, let's leave our picture there because we can use that again. All right, let's take this and let's just move all of it way over there. So we got some space to work with now. So Same idea, but it's actually just like my little what if scenario here. They're saying do the same thing, but let's say that mu is 0.20. So how the heck would we do this? Well, now we do in fact have, this parallel part of gravity is going down this way, but now we have friction which is resisting it. And so friction would be going parallel to the plane, but it would be going uphill. And so here's the way to really think about it. And mine are not matching in size here. Let's see if I can make this guy a little bigger there. So here's the idea. The idea really is if this parallel part of gravity is bigger, the box is going to move, well, downhill. If friction is equal to or bigger, well, the box is going to stay still. Friction isn't going to make the box go uphill, but friction would make the thing stay at rest. So really what I might put here is that if the size, so the magnitude of my parallel force really is greater than the force of friction, well, the box slides downhill. So it slides down. Okay, but if my force parallel is equal to or less than the force of friction, well, it stays still. So now we're bringing in friction. We're just having a look at this one layer deeper. Now, the neat thing is we still just need to find force parallel. We still need to find force perpendicular because that's really the only things we can do right now. We have the same setup. And so again, I'll go ahead and say that, well, sine of my angle, that's really our force parallel over the force of gravity. In the end, we're going to end up having that mg sine of this 22.0 is kind of the way that we would represent this parallel force. But now, in the case of this one, I actually want to go ahead and I want to solve also. Actually, let's kind of write this out though. Now, keeping in mind, we have no idea what m is, but maybe it'll cancel out like it did before. So what I can do is if I put this all in my calculator, I get m times this 9.8, that is gravity, right? Times sine of 22.0. Well, that ends up becoming 3.7 times m, because we still have this m just awkwardly kind of chilling here, right? This really is our force parallel. We have no idea what the mass is, but it's this kind of thing, okay? So let's come back to this, because the idea that I'm hoping we can kind of get to is that we'll find the kind of way to represent the parallel force, we'll find the way to represent friction, and then we can just compare the two because the difference between those will be our net force. That's the whole idea. So now let's find friction, and friction is opposing this parallel force. So from our notes, we know that friction is just mu times the normal force. But in our case, the thing that's fighting the normal force isn't gravity. If it's like on a flat table like this, yeah, sure, then the normal force and the force of gravity have to cancel out. But on this one, the gravity and normal force aren't going exactly in the same directions. We don't have that anymore. Now we have the perpendicular components of gravity is fighting and matching the normal force. So really, the normal force is equal to, but opposite, so it's really equal in size, opposite direction, to, well, our force perpendicular here, okay? And so, well, we might need to find our perpendicular force because we already know mu. So if we could find the perpendicular force, we could then plug it in right here and we would suddenly have friction. And we could then compare friction to this parallel force and find out what the difference is. And we can then kind of set that for Newton's second law, F equals ma, and then we'll have our acceleration. So let's find this force perpendicular. So to do that, if sine got us the parallel part, well, cosine is going to get us the perpendicular part. So cosine of our angle, well, that's just going to give us force perpendicular over the force of gravity. And so doing kind of the same thing here, we know FG, that's just M times G, and I'll multiply it over to this side. And so I'm going to end up having M times G times cosine of our angle, that's 22 degrees, is equal to this force perpendicular. And so kind of plugging in actually 9.8 here with my calculator, I end up having 9.8 times cosine of 22.0. That gives me 9.1 because this has 2 sig figs again. We could go a little, we could keep it at 1 extra sig fig and just round at the very end. That works too. So either we have 9.1 times m, or you maybe have 9.09 times m. So now we have the perpendicular part. Now, what are we going to do with it? Well, this perpendicular part, we said, is equal to the normal force. So we can plug in this 9.1 right here. And so that's exactly what we'll do. So then that means our friction force that was kind of this normal here, well, that's really equal to mu times force perpendicular. And so really that gives me 0.20 times, well, now we have m times 9.1 or 9.1 m. That's what we had here. So 9.1 m. So simplifying my math, 0.2 times 9.1, that gives me 1.8 m. That is the size of our friction force. So now what we've done is we went through quite a few steps already, but now we found the size of this guy, we found the size of this guy. So now we can compare and go, hey, well, this one's bigger, and if the parallel force is bigger, the box is going to move downhill. So now, how quickly is it going to move downhill? Well, we just need to find our net force. So really, we'll kind of set this up with like Newton's second law again. We know that the net force, and this time it's going downhill parallel to my kind of slope here. So our net force in the parallel direction, that's equal to m times a. And we have no idea what a is. That's what we're trying to find here, redoing this, but now with a value for friction is kind of the idea, okay? And so, oops, 0, that's what we're doing. Now, looking at it, the second way that I would write out the net force here in the parallel direction is I would say it's this force minus that force, because those are the only two things in the parallel direction. And I'm choosing to say that the positive direction would be up from my plane and then down the slope. If you chose that the positive direction is uphill, well, you'd end up having that friction would be positive and the parallel part would be negative. So I typically have it so going downhill is the positive direction, or going whichever directions to the right is positive, really is kind of how I like to roll. So we have now the parallel component of gravity minus the force of friction. Well, that is just 3.7 m minus 1.8 m. Well, that ends up being 1.9 m. So now I know the net force. That's really what this is saying. We know the net force is this thing. So what I can do then is I can take this 1.9 and I can just plug it in right there. And so what we'll finally do, kind of getting this guy now, is I'll say that 1.9 m is equal to m times a. Well, we finally have an m that cancels with this one. So in the end, our acceleration is just 1.9 meters per second squared is our final acceleration. That's how quickly this box is going to go down the hill if this is how rough the surfaces are. And we can see that if we scroll over to when we did not have friction, we can kind of take a peek at that one actually, because we did it right here. We had 3.7. So in fact, it is going a heck of a lot slower. And hopefully that makes sense that if, well, that parallel part is fighting something, well, now it's going to obviously go slower down the hill. So now we still have part B, though, to do for this problem. And so for us doing this earlier, we had that this all was A, and then from kind of like here down, it was B. So now we're going to do B right here. So B is still saying how quickly will it be going when it reaches the bottom. So I bet we can do the same equation because we still have all the same things that were given, but now we just have a different, smaller value for A than what we had before. And so I am going to see and just try if we can do this third equation again and see if this guy will work for us. So we have the velocity at the bottom squared is equal to, well, it starts from rest still, so we still have 0 plus, and then we still have 2 times, well, now our acceleration is 1.9, so 1.9 meters per second squared, and it's still traveling 9.1 meters, okay? So if we still have our 9.10 meters here, well, that's going to end up giving me Vx squared is equal to, multiplying these all together, I end up getting 2 times 1.9 times 9.1. Let's take a look here. I get 34.58. 34.58 meters squared over seconds squared. Well, the square root of that is just going to give me, there it is, 5.88 or 5.9 meters per second. So the part B was literally the exact same, just with a different A value. But doing this whole problem with friction took a heck of a lot more than it did doing it without friction. Without friction, we just said, well, the parallel force is our net force. Let's just find the parallel force, set it equal to ma, because that's Newton's second law here. Now, in the case of with friction, we have now these two opposing forces. So we had to figure out this one, we had to figure out that one, we had to compare their sizes and find what the difference in the size is. So we found the difference between these two, and that ended up being our net force. And so once we got that net force and we found it, that let us get our acceleration. So with that, I'm actually going to look at maybe a couple other problems to do. You can watch as much as you would like. They're going to be problems from our review packet, actually. And so that should be pretty helpful in all honesty. Otherwise, you do not need to watch, but I would probably recommend going through and maybe watching some of these, because I'll look at some other friction ones. I'll kind of talk about what some of just the answers are to some of these other questions. Like, for instance here, this problem 53, we should end up getting, I believe, for part A, and let's zoom in a little bit here, and I'm not going to go through all the steps, but we should end up getting for part A that it should go a distance of something close to 1.2 meters, and for part B, we should get a time of around 1.62 seconds. If you get half of that, you found just the time to go up the hill. You need to double it, because then it goes up and comes back. So otherwise, let's just kind of keep going on some of these. So let's look at some of these review problems now that we have here prior to our kind of end of unit kind of practice AP exam, kind of learning check, really. So we got some answers for 1 and 2 here. I want to just kind of skip through those and kind of look at some of these harder ones, in all honesty, such as number 3. Number 3 is a great problem. It has a lot to it, which is pretty kind of cool and neat. And so really what we have here is a 5,000 Newton crate. It's being slid down a ramp that's an angle of 20.0 with respect to the horizontal. We're given the coefficient of friction, and it's saying how much force parallel to the plane must be applied if it slides down at a constant velocity. So slides down at a constant velocity, that tells me that our acceleration is 0 meters per second squared. That means there's no net force. That means that really the push force and friction are like canceling each other out, really, is kind of the idea. And it's also saying in which direction must the force be applied. So let's unpack this a little bit and go figure out like what the heck's going on here. So we'll kind of start just with our picture. So we have like our plane, and our box is going to be on it. And they tell us that, well, gee golly, we know this is 20.0 degrees. And I like to put my box a little bit higher up the ramp because it typically just gives me a little more space to kind of do my triangles and such. And so going straight down, well, that's our force of gravity. And coming straight up off the surface, well, here we have our normal force. And then kind of keeping in line with what we've been doing, well, if I keep going straight off of this, well, here is my force perpendicular, and then here is my force parallel. Okay, now the box is sliding down the ramp. If it's sliding down a ramp, that means guaranteed that friction is going uphill. Friction is resisting the motion of it, okay? Now, here's the thing though. If friction is bigger in size than the parallel part of gravity, it's going to slow down and stop. And that would mean that you would actually need to be pushing it down the hill to kind of help out this force parallel. Now, if the force parallel was greater than friction, it's going to start speeding up down the hill. And that would mean that you would actually need to push uphill to actually kind of keep it going at a constant. So we have no idea what direction we need to push because we don't know if the frictional force is bigger or if the parallel force is bigger. But whichever one is smaller, we need to go in the same direction as that one to kind of rescue it. Because if we kind of help it out, then we can keep things balanced. So we have no acceleration. So we stay at a constant velocity is the whole idea. So really, I guess all I'll say here is if force parallel is greater than force friction, well, we need to push with friction. So we need to push with friction. We need to push uphill. That means with friction. But if our force parallel is less than the force of friction, right? Well, we need to push downhill. We need to push downhill. So that means with our force parallel. We need to make sure that they're even. So we need to help out whichever one is smaller in size. So let's just pick one. We can either pick to go ahead and find force parallel or go ahead and find force friction, knowing that this is also a 20.0 degree angle here. So for me, I'm going to go ahead and actually just try and find my force parallel and my force perpendicular first thing. That's just the first thing I want to do. So let's start out. We know that sine of our 20.0 degrees, that would give us our force parallel over the force of gravity. And we were already given, not the mass of the crate, we were already given the force of gravity on the crate, which is really neat. I kind of gave you one step less than, so you don't need to actually do m times g. You already know fg here. So really, this tells me then if I multiply fg over to this side, which is 5,000, we then have 5,000.0 newtons times sine of 20 degrees. Well, that gives us, when I poke this into my calculator, I get 1,710 newtons. And that is our force parallel. Sweet. Now, let's go ahead and find our force perpendicular, because our force perpendicular right here, well, this is matching and canceling out against the normal force. So if we know the force perpendicular, we know the normal force really, because they match. They're equal but opposite. So they're the same number for their values. And so doing cosine of 20, well, that would give us our perpendicular force over the force of gravity. And so then we would just do 5,000 newtons times sine of 20 degrees. And that gives me a whopping, oops, and that should be a cosine, not a sine. Sorry about that. Okay, cosine of 20, that gives me like 4,700. 4,700 newtons. That is our force perpendicular. But knowing that it's force perpendicular, it is the same again as our normal force. So we really did just kind of find out what our normal force is. So now, the goal was really to compare friction and the parallel part. So let's just go ahead and find friction. We should know either from our equation sheet or from the notes that our friction force is just mu times the normal force. Well, in our case, that means it's mu times force perpendicular. And so really it's 0.400 times 4,700 newtons. So hopefully that kind of made sense. 0.4 times this 4,700, that gives me 1,880 newtons. That is our force of friction. All right, so I want to circle that because really the goal is to compare this to the force parallel and see which side we need to help out, essentially. So they perfectly cancel, so we have no acceleration because we'll then have no net force. So now we know our force parallel though. So wait a second, let's just compare. Well, which one's bigger? Well, force friction's bigger. So if we just let this box go, since friction's bigger, the box is going to slowly slide down until it stops. And then that's going to be it. That's not going to be a constant velocity then. So this means that we must push downhill. So we must push downhill. And it's really to assist our force parallel. So it's saying in what direction must we push. So we already just answered that. We must push downhill. Okay, sweet. Now, with what strength do we need to push? Well, just the difference between these is how hard we need to push. So let's say that to the right is still in the positive direction. Usually we kind of would say that, well, that way is positive and that way is positive. So I'll just say that uphill to the right is positive and up off the surface is positive. So if that was the case, well, we know that we need to push downhill. So I'm going to go and even put a little force FP for push, or maybe it's pull or whatever it is, downhill. Well, if I were to write this out, because maybe you're already looking at these in your head and going, wait, the difference between those is 170 newtons. I need to push with 170 newtons. Perfect. You are done. Now, if I said, what the heck is the work for that? Well, I would say that, well, we know Newton's second law is F net, and this is in really the parallel direction. Well, we know it's equal to ma, but we want this thing to be zero, right? Because there's going to be no acceleration. That would be a constant velocity, right? So, well, I look at the forces here and I go, well, friction's in the positive direction. My push or pull would be in the negative direction, and force parallel is also in the negative direction. We want that to be equal to zero. We want these all to cancel out, right? Again, because there's no acceleration. So that's why that zero is there. Well, if I know this one and I know this one, I can just plug in then. So really that's what those of you that just subtracted between these two are doing in your head. You're going, okay, that makes total sense, because we end up just having 1,880 newtons minus this force push or pull minus 1,710 newtons. And then we go, okay, well, we end up having from this then, we have 170 newtons is our push or pull. And so that's really it. That's how we would kind of write out the steps for it. But it really is just going, okay, well, the difference between these two is how hard I need to push. That's really it. Okay. So I hope that made sense. Let's keep going. Let's look at another one. I can kind of keep going on this, so we'll just kind of chip away through this. So now we have a motorcyclist, and they're coasting with the engine off. So that seems a little odd, but okay. So they're coasting with the engine off at a steady speed of this. But they enter a sandy stretch where the coefficient of friction is 0.8. That's a very big coefficient of friction. And we want to find out, will they emerge from the sandy stretch without having to start the engine if the sand lasts more than 15 meters? And then if they do emerge, what will be their speed when they leave the sand? Okay, so I look at this and I go, okay, well, we probably need like a motorcycle or something. So maybe I just go ahead and we put in like a little motorcycle that we got right here. You can just do a doodle of one. That's fine. And then let's say that it's kind of going along some stretch here. It's going along some just horizontal path. It's just kind of going along. So we'll kind of have, oops, not the motorcycle. Let's make a line here. So there, let's see if that works. Okay, so we have our motorcycle. It's just driving along. It's horizontal. So that's just kind of nice. There's no incline plane, nothing to worry about. We do have friction. We do have friction, and we know that this is the initial velocity, and it's the initial x velocity. Okay, and so looking at my motorcyclist here, we know that gravity is pulling down on them. We know that there's a normal force going up. The engine is not on, so there is no force push that's kind of driving them. If the engine was on, we would have a force that's kind of pushing it forward, but then there is no engine on. And so that kind of makes it simpler. We really just have the force of friction that's kind of acting backwards on this thing and kind of keeping it going. Now, we know also that it kind of has this initial speed. And we go, well, it has to go some distance. Well, will they emerge? How far will they go before they have to stop is really what we need to find. If the distance they need to go to stop is more than 15 meters, yes, they emerge. If the distance when they stop is less than 15 meters, heck no, they do not emerge. So we're just going to go over here, call some distance x. We just want to find out what the heck x is. That's really it. And that's all we're going to do. And so let's go ahead and kind of figure out what our net force is. Now, hopefully you're kind of looking at this and going, okay, well, if gravity and the normal cancel each other out, well, we need to look at and figure out what the heck friction's doing here. So friction really is our net force. It's the only thing that's not being canceled out. So we know that then this net force really just is the force of friction, okay? And we know that that thing is mu times the normal force. But we know that the normal force is equal to the force of gravity here. They're matching. It's on a flat horizontal surface. And we know that gravity is mg. So I can rewrite this a final time as mu times m times g. All right, that's kind of where we're at. So now we know if this is F net and this is F net, the left sides are the same. Well, that tells me then that I can set the right sides as equal. So I can go ahead, I can set these equal because they are both representing the net force. So I look right here and I go, all right, so m times a is equal to mu times m times g. Well, we weren't told how heavy the motorcycle is, but the m's cancel, so we don't need to worry about it anyways. So in the end, we just have here that, well, hey, a is equal to mu times g, so we just have 0.80 times 9.8 meters per second squared. I'm just going to drag this a little bit over here to give me a little more space. And 0.8 times 9.8, that gives me about 7.8. So we have equals 7.8 meters per second squared. So we know the acceleration. Sweet. Okay, well, why do we care? What the heck can we do with this? Well, we want to find out how far it takes to stop is really the idea. That's the goal here. We want to find out how far it's going to make it. It's going to make it before stopping. Or another way we could actually look at this that I just thought of is we know how far it's going. It's going 15 meters. if we can find the velocity at 15 meters, if it's bigger than 0, well, it's still going. It hasn't stopped yet, right? If it's a negative value, that means it has already stopped, is really what that would mean. Because if it's like, if the sand would stop it maybe over here, well, we don't know that this acceleration, like we're just acting like this is always here. Well, if it stops moving, it stops accelerating, is the whole idea, okay? So let's go ahead and kind of look at some of like the equations we might need to do this. Well, if we know how far it's going, x, we know an initial velocity, we now have an acceleration, that makes me think of those unit 1 equations again. So I want to go ahead and actually just find those equations that we used earlier. Where are they? For that first problem. And we're just going to go ahead and like copy them and put them down again. We would just want to kind of put our resources out here so we know what we have to work with, really. So looking at this, we want to figure out how fast it's going when it is gone 15 meters. We want to know how fast it's going. So how fast it's going, that would be Vx. We know its initial speed. We know how much it's slowing down, kind of the acceleration. It's going in the negative direction here because, again, we're going to assume positive is to the right and up. So this really should be a negative a value for it. We'll even put this in green so it kind of stands out a little bit, or maybe not. I don't know. Maybe my pen isn't letting me do green there. But we have no idea what time is. So let's move on. We know how far it's going, 15 meters. We know we get to call this guy 0. We know the initial velocity. We know the acceleration, but I don't know time again. And this is a quadratic we'd actually have to solve. So this one doesn't seem too fun. We could use this one to get time and then plug time in here, and then we could find the velocity. That would totally work. You'd have to use both of these together. But let's maybe look at our third one. We want to find out how fast it's going. So we have that. We know how fast it's going in the beginning. We know the acceleration. We know it's going 15 meters, or hopefully, and we know that we get to call this 0. So I'm going to use this third equation. This is definitely the path of least resistance. It'll be a lot easier. So we have that our final velocity squared is equal to, well, it starts at 20 meters per second. So 20.0 meters per second squared plus 2, and my acceleration, it's negative because it's slowing the thing down. If it's moving to the right, the acceleration is going to the left. So those are fighting each other, absolutely. So negative this 7.8 meters per second squared. That's what we got right here. And then it's going this 15 meters, 15.0 meters. Now, here's the thing. Here's why this is going to work for us. If we do the math on all this, I end up getting that our answer here, let me just do this really quick, 20 squared minus 2 times 7.8 times 15, I get 166. I get 166 meters squared over seconds squared. So looking at that then, that tells me then that our x velocity, how fast the motorcycle is going at the end of this 15 meters, that tells me that it's actually going 13 meters per second. And so really in the end, well, their speed is not 0. It is not 0. And so since they're still going along it, yes, they totally emerge. So will they emerge? The answer is yes. Yes, they emerge. Okay, so with that in mind, is there anything else I want to say on this one? Sorry, I'm just thinking to make sure that I haven't missed anything here. Okay, no, I think that's it. So yes, they do emerge, and we did in fact find their speed as well. So we figured out both parts, and we're actually really done with this problem, which is kind of neat. Now, the other thing that you could do, just kind of throwing this out there, that is kind of neat is you could actually use this third equation. You could use it in a slightly different way. You could kind of reformat it in a way. And so let's say that I took it and I reformat it to find how much it would need to decelerate to stop the motorcycle like before it leaves. What we could do is we could then use this equation, this third one again, knowing then that if we want to make it so it stops, that this thing is 0. And we know the starting velocity and it's going to travel the 15 meters. So how much would it need to be slowing down to actually stop? We could actually have gone through and compared that. And so if I go and kind of do it that way, well, we're going to end up having, and this is just me rewriting this equation, I would have the final velocity squared minus the initial velocity squared divided by 2 times x minus x naught. That is equal to a. And then again, we're saying that if it's stopping right at the 15 meters, well, its final speed is 0. And we know this guy is 0. And so we could go and just plug in here and see that, well, negative 20.0, oops, I forgot my units, meters per second, squared over 2 times this 15 meters that it travels. Well, this is going to tell me that I would need to be going negative 20 squared divided by 2 times 15. I would need to have my motorcycle slowing down at a rate of 13.3 meters per second squared. That's what the A value would need to be to make this guy stop. And so when we get acceleration of 7.8, that's definitely less. And so since it's not slowing down at this much larger value, well, of course, the motorcycle is going to make it out. So that should hopefully kind of help, just a second unique way to kind of check your work and kind of see how you're doing on it. Okay. Let's keep going. Let's do maybe just one more here. And let's look at another kind of challenging one. And it's actually an inclined plane. And it has friction. So we have this 2,000 kilogram car. So this really is our mass. They didn't give us newtons, so this isn't FG this time. And it's at the top of a 20-degree incline here. So our incline is 20-degree incline, and this driveway is 20 meters long driveway. So we're kind of being given an X value. So how far, I don't know, maybe it's going to roll. I have no idea. Well, let's keep reading. It slips its parking brake. Oh, no. It starts to roll downhill. At what speed will it hit the garage at the bottom? So they're asking us to actually find really this final velocity, this Vx. We're probably, in all honesty, going to need to use one of these equations again. We're going to have to use some unit 1 stuff. And this is why we actually try to spend a lot of time practicing with those equations, because they keep coming back. They're kind of going to creep back in for a while now. And we're also told the coefficient of friction is 0.2. So we know mu. Sweet. So let's just draw our picture. So we'll kind of draw our little car on a slant. I like to kind of draw my cars like Dr. Seuss cars, and it's really not that I like to, it's just that I'm a trash artist. So there is our incline, and we're told that this angle is 20.0 degrees. And here is my car here, looking a little Dr. Seussy maybe already with the wacky wheels. And oh yeah, real Dr. Seussy. There. Okay, sorry, that was a little too much. Let's go with something like that. And so it's rolling, and there's a little headlight even. We got a little tailpipe going on here. Okay, so there's our car. Great. Now, same thing. We're going to start with just drawing the forces on it. We know gravity is going straight down. So we have here our Fg. We know also that normal force always goes straight up off the surface. So really, we can kind of like trace it back to here even. It's kind of the idea, the thinking behind it. And we know that it's rolling downhill, so friction is opposing that. So our friction is actually kind of pointing uphill. Then aside from that, we gotta break gravity down into kind of a part of gravity that's going parallel with the slant, kind of in this same parallel direction right here, and then a part of gravity that's going kind of perpendicular at like a 90-degree to kind of our plane. And so here is kind of my force parallel component. So there we go, force, or sorry, not parallel, perpendicular. So here's our force perpendicular. And then kind of going along right here is our force parallel. And from our notes, we know, you don't have to prove this every time, we know that this is also 20.0 degrees right there in the middle. So there we go. Now, the idea is if we want to find the speed at the bottom, well, we need to figure out what the net force is. We need to be able to compare the difference in size between friction and the parallel part of gravity. Because the difference between that will give us our net force, and then from our net force, we'll use Newton's second law, and we'll get our acceleration, and then we can use one of these equations over here from Unit 1 to find the speed at the bottom, okay? Now, I want to mention, if it slips its parking brake, if it slips the parking brake, that really means that it was at rest, right? So its initial velocity was 0. We kind of have to read into that one a little bit. So if I were to kind of put just a sentence here of the approach so that you can maybe go and try this on your own, I would say that really we need to find force parallel, force friction, then find F net in the parallel direction, use that to get the acceleration, and last, use an equation to find Vx, kind of the final velocity of it kind of down the slant. So that's kind of like the general steps, but now we got to like go through and kind of muck through the math to do it, okay? So again, kind of like this earlier one, I just want to start out by finding these two guys. That's the first easiest thing we can do. And so we know M, so really we can kind of find the force of gravity. We know that that thing is M times G, right? And so let's just go ahead and find force parallel, force perpendicular. So sine of my 20 degrees is equal to my force parallel divided by the force of gravity. And so really, if I multiply FG over to that side, we then end up having, and kind of plugging in the same step, I'll have my M times G, that is this FG thing really. So I have my 2,000 kilograms. Oops, sorry, my handwriting looks a little trashy right now. Let's kind of slide this over. Maybe we'll kind of shrink it up here. Then we can kind of zoom in a little bit. So now I have the mass of my car, that's M. Well, 9.8, that's acceleration due to gravity. And then we have sine of 20. Well, poking that all into my calculator, I get like 6,700. So 6,700 newtons, that really is our force parallel. Great. So we're gonna have to come back to this. I want to go ahead and just kind of circle it so it's kind of easy to spot later down the road. Now let's also find our force perpendicular right here. If we use sine to find the opposite, well, that's SOHCAHTOA again, right? So SOHCAHTOA, sine is opposite over hypotenuse. So here's our opposite thing right here. So that was our parallel. Well, that means cosine is adjacent over hypotenuse. So if this one's my opposite, that means perpendicular is my adjacent. And so that's what we'll end up using. We're going to use cosine. So cosine of my 20 degrees will give us our force perpendicular. Our force perpendicular over the force of gravity. And so again, maybe think of it as, oh, we'll multiply FG on this side, We'll do the same, multiply by Fg over here. These two will cancel. That's a great way to think of it. And this force of gravity is just m times g. So now kind of rewriting this simplified, we have 2,000 kilograms. That's the m for my mass. G is 9.8 meters per second squared. So this is m times g. That's our force of gravity. And then cosine of 20 degrees. That gives me, I get, well, I think I must have missed something there. Oh, that's what it is. My cosine didn't work. Okay, like 1,800. So I'm going to just round it to my 2 sig figs because gravity has 2 in it. So 1,800. Wait, that's not right. No, it's 18,000. Extra 0, that's kind of a big deal. Newtons. That is our force perpendicular. And that kind of makes sense because there's a heck of a lot of gravity pulling down on this thing. If gravity is like almost 10, 9.8 is almost 10, 10 times 2,000, that's like 20,000. And so we're pretty close to that. So there we go. We have our perpendicular part of gravity. We have our parallel part of gravity. So now that we have those, let's go ahead and actually figure out what the heck friction is. Now, maybe you're going, why did you even get the perpendicular part? Well, I'm thinking ahead knowing that the net force on this, because I'm not pushing the car, there's nothing like that. The net force is really just the difference between friction going uphill and the parallel part going downhill. So I'm going to write this out as, well, force friction minus force parallel. And I'm again saying this because I'm assuming that to the right and up are positive. So even though friction is going up and to the right, I'm really saying that positive is, well, that way and that way, kind of uphill and off my surface. And that means negative would be kind of downhill here. And so that's why our force parallel is in fact negative right here. So that is the way that I would write my net force. We also know, though, that the net force, and this is parallel kind of to my surface, is m times a. So really, if these two left sides are the same, these two right sides are the same. So I should be able to set these two right sides equal. That's really what I'm looking to do here. So really, let's figure out what the heck this thing is. So we need to find friction. We know force parallel, it's down here. Force friction though. Force friction, that's really mu times the normal force. But the normal force is getting canceled out and is equal and opposite to this perpendicular force. Well, we know force perpendicular, it's this 18,000 here. So we can just rewrite it as mu times force perpendicular. So we can put this down as this 0.20, that's what it is here. And 0.20 and 0.20 both have 2 sig figs, so you don't need to include the 0 there, times my 18,000. And I'm going to move this down a little bit. Times our 18,000 newtons. Okay, well, 0.2 times that, I get 3,600 newtons. So we know friction, 3,600 newtons. So I know friction now, I know force parallel. I can just subtract and find what the heck those are. And I can also set it equal to this MA. So I'm going to do this all kind of in one fell swoop. I'll write it out like this, but I'm going to plug in the values for it. So force friction, so I have 3,600 newtons minus my force parallel, well, that's 6,700 newtons, is equal to m times a. Well, the mass is 2,000 kilograms times a. So this part here is this whole thing. Just kind of making sure that you followed that. And so I end up getting from this that we have negative 3,100 newtons is equal to, actually, let's put this down on a lower line. I get negative 3,100 newtons is equal to this 2,000 kilograms times A. That ends up giving me, well, let's just divide. Negative 3,100 divided by 2,000. I get negative 1.55. And if it's an acceleration, we're doing newtons divided by kilograms, meters over seconds squared. That's our acceleration. So wowzer, what the heck does this mean? Well, it means the thing is speeding up going downhill. That's really what it means. This is our negative direction, and this is how quickly it's speeding up. So now we know, A, what the heck are we trying to do with it? Well, we're trying to find the speed when it hits the garage, right? When it slams into it. So we know the initial speed. We know how far the thing is going. Now we know the acceleration. So let's just find the final velocity. So which of these three equations should we use? Let's look at the first one here. Kind of zooming in maybe a little more. Well, we want to find this guy. Perfect. We know it starts at rest, so that's 0. We know A, excellent. I have no idea what the time is, though. I don't know what that is either. So let's keep going. We know that it travels 20 meters. So we know that. That tells us up here. That's how long the driveway is. We know we get to call it 0 wherever it's starting from. Great. We know that this guy is 0 because it starts from rest. So that's pretty convenient. And we know the acceleration. So we know this. So what I see so far is I could use this second equation and get the time, plug the time in here, and then get the velocity. That's what I see that we could pretty easily do. It wouldn't be too hard. No quadratics. That'd be kind of nice and friendly. But let's just check the third one just to be safe. We want to find how fast it's going at the bottom. We know it says since it slipped its parking brake, it started from rest, so that's 0. We know the acceleration. We know how far it's traveling. It's going down the 20-meter long driveway. And we know we get to call wherever it starts 0. So actually, even though using these two wouldn't be too bad, still using the third one is much easier still. So I'm going to go ahead and use that one. So I get that our final velocity squared is equal to 0, because it was starting at rest because it slipped its parking brake, plus 2 times, now it's negative 1.55 meters per second squared is our acceleration, and it goes 20 meters. Okay, and so in the end, and now maybe you can already spot that we're going to have to take a square root of a negative. That's a little weird. That's a little odd. Well, if we called where it started over here 0, it's moving downhill. So that actually means that it's going to travel 20 meters in the negative direction. So you could either fix this by putting a little minus sign right here at our 20, or you could just go, in the end, we know I'm just going to find the speed, so I'll just forget any negatives. This is the slightly more correct way, kind of having that the 20 meters is a negative there. And so in the end, I get that we have 62 is exactly what I get for our velocity squared. So 62 meters times meters, we have meters squared over seconds squared. And well, the square root of that just is 7.87. So rounding it again to kind of 2. Actually, we should have 3 sig figs here. So this should be actually 62.0 meters squared over seconds squared. And the square root of that ends up giving us 7.87 meters per second. And it's going downhill. And since we said that positive was uphill, this better have a negative sign, because we could take negative 7.87 and square it, and we'll get 62. We could take positive 7.78 and square it and still get 62. So you still have to think about what the heck should the sign be at the very end here. And so that is how fast our car is going when it hits the garage at the very bottom of that driveway. And so with that, I'm going to hold off on doing any other problems. I will just mention that this last one, you should get like a 19.7 for it, and you'll have to convert that 50 kilometers per hour. So thanks for sticking around for whatever you stuck around for. I hope that helps, and write down where you have questions, concerns, things don't make sense.